first introduce myself. So again, I work for LinkedIn. We're based in New York City. We have our offices in the Empire State Building, where we have probably about 1,000 people from LinkedIn who work in the building, and the team of software engineers there is about 90, which has been steadily growing over the time that I've been there for the last 3 years. And what I want to talk about is two systems. So what are these two systems? So this is a story of a not at LinkedIn, not at Google, but a system that I did work with. And we had a situation where a system that was functioning, was working in production, and it was starting to reach its limits of capacity, that it could no longer handle the size of the input that we were giving it. And so we needed to create a new system to replace the old system, and we wanted to fix the problems that were getting in the way of the system being able to handle the larger inputs. This is an example of an anti-pattern, which, as I'll explain where it went wrong. The important thing about an anti-pattern is it's an example of something not to follow, but it isn't just a story where you say, oh, look at this, look at these people, they did something stupid, ha ha ha, let's all do better than that. The important thing about an anti-pattern is that it's a team looked at a problem and they sought a solution and they found something that looked like a solution, but once they actually followed the path down, it turned out that it was not a solution. And so what we're trying to learn from it is what made it look like a solution and how not to fall into the same trap. And what I want to approach here is what we're trying to learn from this. For all of us here who are coming to this conference, what we want to learn about is how to become better developers. And what is it that makes someone a better developer? I'm using the analogy here of a coach versus a rookie, where as a person becomes more experienced, they obviously understand things come to become better at what they do. But how is it that you become better? And what makes, so the analogy here is, imagine that a coach and a rookie are sitting and watching a football game together. The question is, are they both seeing the same thing? And they are really seeing the same thing if you're just paying attention to what they're seeing visually. But if you were to ask each of them, what kind of play was that? What kind of defense was that? Which player was out of position? The person who would be more likely to be able to answer that question intelligently would be more likely the coach, because the coach has a deeper understanding of the game. And so even though the coach and the rookie sitting next to each other are seeing the same things, the coach understands it better. We were just learning about artificial neural network models. What is in play here is about conceptual models that go into our brains. And that's our tool that we can become better at what we do, because whereas you can have GPUs and faster computers and more of them to make better neural networks, we're kind of stuck with our neural networks that we already have. And in order to make them work better, what we need is better models, better conceptual models to make better use of what we can do. So the active part of what makes the difference in this is the software architecture. When you have a system fulfills certain requirements. It has certain functionality that it does. But one kind of requirement that is in a system are ones that are involved with the architecture. The architecture being the high-level organization of the system. And in some ways, this can become the most fundamentally important area of the system, if for no other reason, because it's often the most difficult thing to change after the fact if you get it wrong. And so when you look at a set of requirements for a system, what you're actually looking for is a set of requirements that will have the most impact on the architecture, because these are the ones that you're going to have to think about the most in designing your system in order to get them right up front. If they're ones that are not architecturally significant, you have more ability to change them later. And the one area of these that I want to focus on out of all the areas is the quality attributes. They happen to apply very strongly in this area, but this is a conceptual model of your system that's different from the other kinds of requirements. Because you might have a requirement that says your system needs to have the following functionality, needs to be able to send an email, needs to be able to download a file, or whatever other functions you might have. And you'd be able to look at the system and see the module of this is the one that downloads a file from the internet, this is one that saves it to the disk. But if you are seeking out something like scalability or performance or security, there's no performance module in your system. These are attributes of the system that exist in a different level than in the components, in the model, in the code. So let me try to give an example of what I mean by quality attributes. Because let's say you have a system that you're trying to build, and this is not a computer system, this is a system for making smoothies. So what you need is some kind of device for making smoothies. You might choose a blender in the kitchen. It has a lot of, it's good at doing the task, but it has some drawbacks to it, which also you have to bear in mind, which is, for example, if you wanted to take it out on a camping trip and make smoothies out in the forest, you would not be able to use this blender because you'd have no place to plug it in. So you might seek a solution for what's a better solution if I want to have a blender that also can blend when I'm not in the kitchen or away from an outlet. So I could use one of these, cordless, rechargeable hand blender. It can also make smoothies, and it can do it without being plugged in. Of course, it has some drawbacks. It's, despite the fact that it has these extra features, it has some drawbacks in that it's not as powerful. It is something you have to hold in your hand the whole time. You can't just push a button and walk away from it. And you have to recharge it after a time, and after that it doesn't work anymore. So perhaps you want something that combines the best of both worlds. You have something with power and something that also has the portability that can work outdoors away from an outlet. So you could go get the chainsaw blender, which solves your power problem because it has a powerful engine. However, it has some cons that you might want to bear in mind before you get one of these. And in case anybody actually does want to get one of these, it's not a product that you can buy at Walmart, but there's an instructable link online where you can learn how to build one yourself. And if you do, and you want to go on a camping trip and make smoothies, I will stay far away from that, but it is something that exists. What you see from this is that here are examples of 3 systems that are all designed to do the same functionality, but they do it in a different way, and they have different trade-offs of pros and cons for what they're able to do. And choosing which one is the right one that you need for your purpose depends on what your purpose is and what attributes you need from the system that you want to build. So let's look at the system that was actually the computer system that was built. In a very high-level discussion, all this system was doing was something called aggregation. You had a set of input files. Input files have records in them, and the records are each of a certain type, which the type comes out from the processing step. And the job of the aggregator is to take each of the inputs of the same type and to combine them together so that in the output, all of the records of the same type are combined together. And this is a diagram of what the system actually looked like. You had a set of work. The distributor sent them out to a network of computers that all did the work. And at the end, the aggregator was sitting at the end collecting the outputs and writing them out to disk. And here's basically the problem that was happening. The aggregator was getting overloaded. So what was going on? Dug into a little bit. There was nobody on the software team who had actually built the aggregator, so we had a little bit of detective work to figure out what was going on. And what we found was it was ending with an out-of-memory error. And it seemed odd because all the tools that we had indicated that there seemed to be plenty of memory left. So why was it running out of memory? And we saw that somewhere along the lines it was allocating 500 megabytes in a single chunk, and that was failing. And the question is, why in the world was it doing that? And what was it that we can do about it? So here's a little background of what the problem was. This was a Windows 32-bit system. And in 32-bit Windows, you have a 4 gigabyte address space for each process. And 2 gigabytes of that is reserved for the operating system. And each one of the user processes gets its own 2 gigabyte address space to run its own process in. And the problem that we were having is that this file writing system was using a memory mapped file. And the way a memory mapped file works is you have an area of memory. If you're familiar with the way virtual memory works, you have a certain amount of RAM, you start using it, and then you run out of RAM. So instead of just your program terminating, you'll take some of that data in RAM and you'll have this virtual memory manager. It'll write some of it out to disk and then free up some RAM to bring in, to do some more data. And then when you need that, if you try to access that memory again, it'll bring it back out from disk into memory. So memory mapped files work in the opposite direction. You take that address space and you map it onto a file on the disk. And every time you want to write to, every time the system writes to that area of memory, the memory management hardware will find that spot on the disk and swap that data in, and it'll keep it around until it's ready to swap it back out. And it's actually a very efficient way. But the problem is that with the size of this file, it was no longer able to get a contiguous address space to allocate. So the system was terminating with an out of memory. Even though there was memory left, there wasn't a window large enough to contain the whole output. So this is a problem because you see that there isn't much that you can do about that if you're running in this environment, other than try to push some of that memory out of the way. But at a certain point, you're reaching this problem where the file is just too big to fit in the address space that you have. Two quick takeaways to get from this. One is, if your system is already blowing up and you're already having a problem, this was probably too late to start noticing that you had a problem. And also that this is the type of problem, which is the class of problems where you can't solve anything by getting a bigger computer. A faster computer with more RAM isn't going to solve the problem of this 2 gigabyte address space. So the team looked at the problem and said, okay, let's fix it. The problem is that we have a scalability problem. We're running out of memory. We aren't able to scale to the input sizes that we want. We need to build something that can scale better than what we already have. So they said, let's go get something that is more scalable. So we found this thing here, which is in-memory distributed data cache, which I won't mention precisely which one it is, but we can nickname it the chainsaw. And it is, what it is that it's a bunch of computers all connected to each other, and they all have the data sitting in their memory, and you can access any one of these, connect to any one of these computers and request the data that you want, and if it has it, it'll give it to you, and if it's stored in one of the other computers, it'll go fetch it. And what's good about this is that it's fast. It has this ability that you could actually take one of the machines out of the cluster and the whole thing will keep on running, which is something that you couldn't do with the old aggregator solution. And it's also scalable. You can always add more machines to the cluster. So this has lots of attractive capabilities that the old system didn't have, over and above the problem of that it can handle the larger input size. So they went and they implemented, oh yes, and this is another example of how it is scalable. And so what they did was they said, well, let's fix our problem. Our problem was with the aggregator. So let's replace that aggregator in disk with aggregator and in-memory distributed cache. So now we'll get the scalability that we need, and we won't have that problem of that memory map file running out of address space. And we see here from the graph that we're able to do input sizes that are a lot larger than we were able to do before. See the empty space over here because the couldn't run on the size input before. But there's a problem here. I don't know if any of you can spot it, but the new system takes longer to run than the old system on the same size input, which in and of itself is not necessarily a problem. But there's this word up here that says nightly batch. And what used to take you 6 hours to do now takes you 24 hours to do. And this is a problem with a nightly batch system, in that nights are slightly shorter than 24 hours. What do you do now? So where did we go wrong? So the problem, where we went wrong is that we noticed that we had a scalability problem, and we immediately tried to attack the scalability problem. And we didn't notice that there are other things in play than just the scalability problem. We knew that we were reaching the limits of the constraint that we had in memory, but we didn't notice that there are other important constraints in the system. There's time constraints, and there are other important constraints, and we should have stopped first to first list out what are all the important constraints of our system, including the ones that aren't currently a problem, and then evaluate the potential solutions and whether it meets all of the important constraints. And in particular, if you look at quality attributes, scalability and performance are things that are often trading off against each other. You can't easily affect one without also affecting the other. So where exactly was it going wrong? So let's look at the original system. So the original system has some differences from the replacement system. If you have a bunch of workers, and let's say they're all currently writing the same red record, this is a very efficient scenario in the original system. Because you have a limited amount of memory, you can only have a certain amount of the file in memory at any given time. But if you're all writing at the same record, you have the ability of having it all in cache, all in memory. All of these writes happen very quickly in an in-memory situation. And whereas if you have a bunch of workers connecting to this cluster, assuming they connect to some random node in the cluster, you have this problem, which is that if each one is writing to the red record and they're on different machines, in the background, this cluster is going to let you do that, but it needs to know that the write is over here. Before this one can modify it, it has to transfer the data over to the other one. And so this background synchronization is all this extra overhead that is happening in the cluster that you're supposed to, it's supposed to be sort of invisible to you, but it's not invisible in terms of performance. In addition, if you decide to solve that by always writing to say the same node, that doesn't fix everything, because the problem is that if everyone writes to the same node, that node becomes a bottleneck and you get none of the extra performance from the other nodes in the cluster. So clearly you have to handle this in-memory data distributed cache differently from the way you handled the aggregator before. And in the analogous situation where on the original system where you're just writing to records randomly, that's actually a slightly worse performance situation on the original architecture. And so anyone who was being conscientious about performance on the original architecture would try to avoid writing random records because that causes more swapping to the disk. So having just replaced just that one component led to this problem that it doesn't behave the same, it doesn't have the same trade-offs when you use it that way. A better way to have used the cluster would have been to try to make some localization so that the workers can connect to different nodes, but they'll pick which node strategically so that all nodes of a same type of record all records of the same type of record will get written through a particular node. And that way that'll reduce the amount of background synchronization going on, and will also allow you to make use of the full cluster and get the scalability attributes that you want from it. So the conclusion about this is that thinking a bit more about the architecture, in particularly the quality attributes that you are seeking to fulfill, helps you get a better start for evaluating a potential solution as to whether it's going to fit the problem and solve the problem that you're trying to fix. And it's important to pay attention to these things like quality attributes in designing your system, because in the end, the architecture is the hardest thing to change, and a little bit of thought up front will save you a lot of rework time on the back end. Thank you.